work. It doesn't seem.
Yeah.
I like doing these videos for you guys, but then it's. Is that gonna work at all?
Yeah, it'll work, but we're kind of missing your face a little.
My face?
It gets the whole board, but oh, there you go.
Oh, as long as you get the whole board.
Yeah,
I'm standing in front of the board.
Yeah.
Okay, should be okay. Okay, and it's recording?
Yeah.
Okay, great, thank you. Let's see if that will actually work for us. Okay, so I have these two spaces. I would like to show that, and they're each going to use the, all of these intervals are relative to the real numbers under the absolute value topology. I want to prove that these are homeomorphic. Prove that A and B are homeomorphic. Okay. So homeomorphism, the definition means that there should be a function from A to B that is a bijection and which preserves open sets in both directions. Okay. So it's a little different. If I just gave you one interval and one interval, that would have been like a problem we would have asked you a few weeks ago, and you would just go from here to here, right?
I think it's good.
Okay.
Something came, but
It's okay. Okay, great. Okay, so what do you guys think about this? Can I suggest a hint here? Do we need a hint?
Yeah.
How about we just try to find a homeomorphism from 1,3 to 2,12, and then we'll try to just find a homeomorphism from 5,8 to 5,17, and then we'll go from there.
So we need two different functions.
So we need two functions. Let's try and define two functions. So let's define a function f that goes from 1,3 to 2,12 via. Now, does anybody know how to get a nice bijection here?
Times 3 minus 2. Minus 2. Times
Formula?
5 minus 2.
5.
So 5x minus 2.
5x minus 2.
Minus 3.
3. Sorry.
Minus 3. 5x minus 3. Let's just see what that gives us. So I just like to check the endpoints because it's a linear function. So if I plug in 1, I'm going to get 2. And if I plug in 3, I'm going to get 12. Okay, great. So there's a function. And let's define g that goes from 5,8 to 5,17 via, anybody got a answer for me here? By the way, if you're wondering how we come up with these, basically, you want g of 5 to equal 5, and you want g of 8 to equal 17, and you just use these 2 points to then, so you have the point 5, 5, and you have the point 8, 17, and you literally just try to make the line that goes through those 2 points. So the slope of this line is, the difference of the y coordinates, which is 12, minus the difference of, divided by the difference of the x coordinates, which is 3. So the slope is 12 over 3, which is 4. So we're looking for, 4x and then plus or minus something, right? Well, when I put in 5 for x, I'm supposed to get 5 as the output value. So, well, this is 20, so I have to subtract 15. Okay? So that would be the formula. Does everybody see how I'm getting that?
Yes.
Okay, so you just literally use like high school algebra to find the equation of the line that goes through those 2 points. Okay? All right, so we create those two functions. Now I would like to note that f and g are, well, first of all, they're bijections. Are bijective. I think we can say that that's clear. They are linear functions that match up at the endpoints. So these are bijective functions. If you really wanted to, you could prove one-to-one and onto from the definition, but let me just leave it like that for now, okay? And what else do you suppose I'm going to say here?
They're continuous.
Right. So they're bijective and continuous. How do you argue that they're continuous?
Because they're straight lines and are.
If we're just using the absolute value topology on the real numbers, this is really a math 350 function. And so anything that's a polynomial or a linear function is going to be continuous. So now, if it was a strange topology, if this was not using the regular math 350 topology, we would then have to consider pre-images of open sets being open and so on and so forth. But in this case, I'm perfectly happy saying that this is since they are lines in the real numbers with the absolute value topology on them. So those are bijective as well, okay? So we have that, and also, if you look at F inverse and G inverse, which would be the functions that go in the reverse directions, those are also going to be lines, right? Remember that if you wanted to actually get the equation, you would just simply set y equal to 5x minus 3, reverse the x and y, and solve for y again. And you're going to get another line. So you'll be able to also justify that that's continuous by the same reasoning. So these are continuous as well. Okay, so therefore both F and G are homeomorphisms. Okay? Now technically, if we didn't care about the specific homeomorphism, we could have just said that from class, we know that any two open intervals are homeomorphic. So we could have said this is homeomorphic to this from class. This is homeomorphic to this from class, right? But here, I actually think it's useful to write down the homeomorphism, the explicit map that's giving me that homeomorphism. Okay, so F and G that we've constructed are homeomorphisms. So we have these homeomorphisms here. So now the question is, how do we actually prove that A and B are homeomorphic? So define a homeomorphism from A to B via. So now my question is, how are you going to do it? How are you going to give me an input from this cross product and give me an output from this cross product?
Couldn't you just use something like on the take home?
For their kids.
Exactly.
Take home, you see it.
You guys have already been working on the take home. That's great to hear. No, and if you've done it on the take home test, and then this was a question on the midterm, you could absolutely just immediately quote that from the take home test or from something you've already proved. You can create what I call the cross product function, right? F cross G from A to B via F cross G of let me just call this X and Y here. And the way you do it, so this is X is somewhere between 1 and 3, and Y is somewhere between 5 and 8. And then my output is just going to be the ordered pair F of X, comma, G of Y, right? Mm-hmm. And that's exactly how on the take-home test the F cross G function is defined on that one problem. And what you proved on that problem, I believe, was that this is continuous, right? So this is continuous, so note from the take-home.
Could you explain it though?
Nice try. From the take-home part of the final, F cross G is continuous. continuous. Okay, so we got that. Did you prove anything else on that question? I can't remember. Did you have to prove it was a bijection? I just said prove it's continuous. Okay, so technically we also have to show that this is a bijection and that the inverse function is continuous as well. So there's a little bit of work that goes into this, but let me see. So the reason, it's, okay. Actually, the other thing you can do, instead of showing that it's one-to-one and onto, another way of showing that something's a bijection is literally to just construct the inverse function, right? So
it's the same.
And then show that when you compose the function with its proposed inverse, that you get the identity map. Right? You guys remember that? Yeah. Okay, so you could also, we have, I could write it as F inverse cross G inverse, which would be going from B to A via F inverse cross G inverse of X, Y equal to, what you would do here is you would just take the inverse of the X part under the F map and then the inverse of the G part under the G map. And because F and G are already bijections, so we already know that F and G have inverses. We didn't write down we didn't actually solve for what the formulas were, but they would be, these would again just be two continuous individual functions that are bijective. So you're going to have, when you compose this with the original F cross G, you're going to get the identity map in either direction. Okay? So by the take-home test again, which I won't go into the details of that, but by the take-home final, this is also continuous. Do you guys want me to show more about the bijection here? Or is it clear what I'm talking about? So this is also continuous and a bijection from B to A.
Like, if on the test, would you actually want us to plug it in and then prove it, or can you just say, since the inverse?
I would probably just accept that it's clear that if you're taking two different functions that are already bijections and you're just putting them into two slots, that function will be a bijection. I would be okay with that, but I just want to make sure everybody would be okay with that. It's like, for example, if you were trying to prove that this is onto, technically you would pick an arbitrary element over here. Well, that's fine. F is onto, so you can find a preimage for the first slot, and G is onto, so you can find a preimage for the second slot. That's how you would prove explicitly that this is onto, right? And similarly, one-to-one would follow because both F and G are one-to-one. So maybe I won't write all of that down. That would really be a Math 280 proof. Like, I could ask that question in Math 280. It's not really topology. Okay, so this is continuous and it's a bijection. And so, therefore, F cross G is a homeomorphism. I think that's pretty much everything we need. We've got the original function F cross G is continuous. We found an inverse function for it, which is also continuous. So we have a bijection, or we have a homeomorphism. So F cross G is a homeomorphism. Okay. So does that make sense, what we're doing there? Okay. Can I erase over here a little bit? Let me see. A couple other things about this, maybe. So, here's a quick follow-up. Is the interval 1, 3 cross 5, 8 homeomorphic to just 2, 12? Just one single interval by itself. Something worth thinking about.
No.
Got a vote for no already? Okay, how come?
Because on the second, so if you have like x and y in A, then you would have to map the y to the empty set, right? Or to nothing?
All I have to do is find one valid way of defining a function from here to here. And maybe it's not the way you were thinking of. Maybe there's some other way to do it. I can't assume what the form of that function would look like. I could assume by way of contradiction. I could say, by way of contradiction, suppose that there was such a function. So from 1, 3, cross 5, 8, going to 2, 12, I could suppose that this is a homeomorphism. But I can't say specifically that, oh, well, that means the second slot has to go to the empty set. I can't do that. I do like your answer, though. I think the answer is no. But I want to know what's wrong.
Is it because there'd be no way to get like the inverse to get back?
There'd be no way to get an inverse. If there's no way to get an inverse, then you're claiming there's not even a bijection. Okay. So is that the basic idea here? Let me ask you this. Is there a bijection from R cross R to R? Can you do that?
Yes.
I think yes.
What's your function?
X plus y.
X plus Y?
Yes.
Oh,
So what's f of 0, 2? What's f of 1, 1?
that's not.
It's not 1 to 1. Da-da-da.
That's not.
The answer is these are not the same cardinality. They're not the same cardinality. There is no bijection. They're not the same size infinity. In the same way that there's no bijection from the integers to the real numbers, because one of them is countable and one of them's not. Now here, these are both uncountable, but this one is more uncountable than this one, if I could say it that way. So there is this homeomorphism would imply that we have a bijection, and there is no bijection. There is certainly a bijection from 1, 3 to R, and from 5, 8 to R, and from 2, 12 to R. So I can actually just replace this problem with this one. Is there a bijection here? And the answer is no. Okay, but this means F is a bijection, which is impossible since 1, 3 cross 5, 8 has a different cardinality than 2, 12. I'll be honest with you, this would not make a good test question, because the issue with this lack of homeomorphism isn't really the topology part. This is just about cardinalities of sets, which we really didn't spend that much time talking about. I mean, I didn't really go over this kind of stuff that much. So it's not the greatest question, but I just thought I would mention it while I was at it, that yeah, it is possible to disprove a homeomorphism by just showing there's no bijection. That actually leads me to another question that I was going to ask you guys, if I can find it. Oh, yeah. So I think I'm ready for number 3. Is everybody ready for me to go on?
Yes.
Okay, so number 3 here is just going to say, give an example of a topological space x comma tau such that x cross x is homeomorphic to X. This one has a really easy answer, but you have to think of the right thing to put together here. Do you think you know it already? Or do you have any comments about it?
Yeah, I guess U integer cross integer is homomorphic to integer.
Okay. So I'm glad that you use an infinite set, because obviously with a finite set you can't do this, because in a finite set x cross x won't have the same size as x, right? But when you're talking about a countable set, such as the integers, when you cross two countable sets together, you get another countable set. So at least Vin has given me something that I could create a bijection. Okay, now what topology do you want to use? Because I need to know what your topology is to know if it's a homeomorphism. I have to know what are my open sets.
So I'm gonna to use this. I think discrete topology. Discrete topology is for both.
Okay, so let's let x equal z. And for tau, you want to use the discrete topology. Let's try that. Okay, and then, so your function then, you have some homeomorphism here that you're trying to talk about. So there is a bijection. So you could say, well, I'm going to take any bijection without actually writing down a formula for f. We can just say, well, there is definitely a bijection between these two spaces. Now, does it preserve open sets? If I take an open set here, and you're telling me you want everything to be open, the pre-image of it over here, well, if I don't know the formula for f, then I don't really know what specifically, if I take an element from here, I don't really know what its pre-image would be. But I do know that its pre-image is some set, right? And you just told me you want to use the discrete topology on Z, right? So now what do the open sets look like in Z cross Z? Well, basically unions of open sets like this, right?
Union cross.
So every point is open.
So is everything in here open?
Okay. Yes.
Yeah, because if I take any point, for example, let's just say I take the point 3, 7, right? Well, 3 is open as a singleton because it's going to be the pre-image of some singleton over on this side. Well, actually, hold on a second. What I basically mean is, because this is a bijection, this whole point will be the pre-image of some integer. So any singleton integer over here is open if we use the discrete topology. So then this being its pre-image will also be open, right? So actually, no, I'm still not saying this right. I'm trying to argue that this is open, given that I've started with something open over here, right? So I start with an open set. I can choose it to be the image of this point if I want, because this is a one-to-one onto bijection. So this point is the pre-image of some singleton. The singleton is open here on this side. The pre-image of it is this point. How do I know that this is open? Remind me again.
Discrete topology, so everything is open, right?
Well, it's the discrete topology on Z. Okay, so now what's the topology on the Cartesian? What's the product topology?
It's tau
Union
cross
of all
tau.
the bases.
So it's tau cross tau. So we have a basis for this topology, which consists of basically taking anything open from here, cross with anything open from here. So I can view this as 3 cross 7 essentially, right? This is the point. And this is going to be open because it's and single because everything's open. This is open because everything's open, and I'm taking its cross product, so therefore this is open. Okay? Great. So basically, let me just write something down for the notes on that. So we can find such F that is a bijection, and given any open set U inside of Z, its preimage, which would be the preimage of U, is open in Z cross Z, since all singletons are open in both Z and Z cross Z. So, to tell you the truth, this would have been a little easier if we would have used the trivial topology instead. Because if you use the trivial topology, then we actually proved it in one of the homework problems from 4.6 that we kind of did together in class on the last day. I said, look, if you use the trivial, so if you take the trivial topology on this space and on this space, then the topology that you get, the product topology, is trivial. The thing about using the trivial topology is, I mean, if you put the trivial topology here, what do you have to check? The preimage of the empty set and the preimage of the whole thing. The preimage of the empty set is empty. The preimage of the whole space is the whole space, if it's a bijection. So that would actually have been slightly easier, but this is fine. This works just great as well. So.
Can we actually talk about like a specific function, like especially if you use n? Can't you like map like 1 1 to 1, 1 2 to 2, 2 2 to 3?
Yeah, I don't want to spend much time on this because this is actually kind of technical to write it out. But you basically what you do is a little diagonal argument where you kind of do this. You go along these diagonals. So I actually normally would define the function the other way. So f, I guess I can just define it this way. So f of 1, 1 would be 1, and then 2 and 3 like that, and then 4, 5, 6 like that, and so on. Mm-hmm. This is a classic argument for how to make a bijection from a set to that set crossed itself, in the case of a countable set. See, it doesn't work for the real numbers. The real numbers cross real numbers are not homeomorphic to the real numbers because you can't sort of put the numbers in order like this and list them. So, but anyway, that's a little bit off the mainstream of what we're trying to do here. Okay, let me just see do what else I want to do. Yeah. Oh, I know. Let's do something, a little bit of an older problem here. Something from a little bit earlier on. Okay, so here's what I want to do. So here's another example. What number 4? I'm actually going to prove that every metric space is actually normal. Now, the one that you're learning for the final, one of the theorems for the final is that every metric space is regular. So it's actually very similar to this, but I'd like to just try and prove that every metric space, let's give it a name, let's call it x, comma, d, like that. Let's try to prove that a metric space is normal. So we have to remember what normal means. That's going to be worth some points just to know the definition, of course. So what was the definition?
T1 and T4.
Right. So assume xd is T1 and, sorry, we need to show.
It's T1 and T4.
Yeah, sorry. We need to show. Yeah, assume that it's T1 and T4. Then we're done. Okay, this is what we need to show. Okay, so, and does anybody remember how we can just show T1?
Yes. Every metric space is Hausdorff, so it's T1.
Okay, so from the homework, right, a metric space is always Hausdorff. Okay, so it's always Hausdorff, which is T2, so hence it's also T1. Okay, so I know we just had a test like a couple weeks ago. You have to know the relationship between T0, T1, T2, T3, T4, regular and normal. All of those definitions. Just go back again, make sure they're still clear in your mind. But definitely T2, which is what Hausdorff is, implies T1. Okay?
Can
Question?
we also say that singletons are closed in a metric space?
Yeah, you could also just say in a metric space, singletons are closed, and that's fine. Yeah, because the complement of a singleton would be open. You just say it that way too. Yeah. Okay, so now I want to show T4. Can you guys remind me what the T4 property is?
Disjoint closed sets.
Okay, I'm going to call them F and F prime. So assume F and F prime are closed and disjoint, right? So for T4, we're going to, so this is for T4 right here. To show T4, I'm going to suppose I have two disjoint closed sets. And what is the job ahead of me here? So here's F, and here's F prime. What do I need to do?
Disjoint open.
And two.
Okay, we need to show there exists U and V in tau, they're open, right? With,
F is a subset of U,
oh, sorry. F is a subset of U.
and F prime is a subset of V,
F prime is a subset of V.
and the intersection of U and V is empty.
And, right, the intersection of U and V is empty. So we want to show all of these things right here. Okay, let's see if we can do it. Okay, so that's the starting point. So we have two closed disjoint subsets, F and F prime. I've got to come up with the U and the V. Okay. And we're in a metric space, so there is a metric D that we haven't really been talking about so far, but we're going to need to make this proof work. Okay. So I'm going to to help you with this, I'm going to give you a definition. If I wanted to ask something like this on the test, I would give you the definition. So it's a little terminology that I think will be useful to do the proof. So given A inside of X, if we take a subset of X, I'm going to, for every little x in the capital X, I'm going to define what I'm going to write is capital D, so the capital distance from X to the whole set A. So from a single point X to the whole space A, this is going to be defined as the infimum of the capital D distance from little x to little a, where little a runs throughout the whole capital A. Okay? That may look a little familiar from the take-home test, but it's not the same. It's actually not the same at all. So this is a whole set together with a single point right here. Okay? So we have that. We'll just kind of make that as a definition. Okay? Okay. So how can we make an open set around capital F, open set around capital F prime? So we take a point from here, point little y, right? I'd like to kind of make a neighborhood or something, right? A neighborhood will be open, yeah. So the idea might be just